All right, great to be here. I too was a Michelson Fellow right before it was reincarnated as a Sagan Fellowship, so good to be here. So I will focus on validation and characterization, which is the strength of TTVs. Transit timing variations. All right, so this is a plot that shows us all the variety of different detection techniques and tries to categorize them. You have the dynamical branch, the microlensing branch, and photometry branch, and then just miscellany. So the two most successful techniques so far are very related to each other: radial velocity and transit. Not related in concept, but related in confirming power, because as we just heard from the ground-based experiments, 1 to 2% of candidates turned out to be confirmable, and that was mainly by radial velocity. In a few cases, it's gone the other way, where radial velocity discovery was later seen to transit. So I'm going to take you down this path, but go a little further down to transit timing variations. So this is a technique where you see the transit of the planet, and then you see that the transit is not steady after all. If you do the Boxley squares algorithm, you might fold it at a particular period and find the planet, but then a few months later, you see it's marching away from the phase that you folded it at. And we'll see how that works. And then it says CTTV. So whoa, it spans this big gap as well. So the TTV is actually a dynamical technique, and it can get you down. This axis is decreasing planet mass. So it can discover planets down below a Jupiter mass, and it has characterized planets well below an Earth mass. And we'll look at that. So this is out of date, but to really keep track, you'd have to make this every like 2 months to track the progress in each of these in these categories. All right, here's the haul of more than 4,000 candidates from Thompson et al.'s analysis of the Kepler data. So this is now giving a reliability score based on the data itself, like those centroid offsets and whatnot. So you see that the large planets at any period really are pretty reliable, and then the reliability goes down as you go towards the signal to noise limit. Raphael has suggested that it's harder to find a planet when there's multiple planets transiting. That is maybe the case, although the planets cover the star very seldom, a small duty cycle, small fraction of the time. So if you find one planet, you can remove it and have most of the data to look for another planet in. Of course, you have to look at all those different peaks in the BLS spectrum. But once you find a system with many planets transiting the star, well, you don't probably have a cluster of binary stars behind your target star. So if you really have multiple transit candidates on one star, it's probably really a system of planets. And in fact, we found hundreds, over 500 systems of planets. And here's a video I made of these from the Kepler mission. It's called an orrery in honor of the brass mechanical devices that describe the solar system. Here's the inner 4 planets of the solar system for scale. And so this is 1 AU, and that's the scale of the planet. So you see the color scheme is just the red is the innermost planet, and then the more colorful the system gets, the more planets there are. So this is Kepler 90, Kepler 11, which we'll talk about in a few slides. So of course, most of the planet candidates are single, but then the next most common is doubles, like this guy. And then this is the rare 7 or 8 planet system. Vanderberg sitting over there saying, that's an 8 planet system. All right, so we zoom in now, and these are the smaller and smaller systems. Still here, we have some 5 planet systems hugging right into their star. The smallest stars are the densest, and therefore can have the shortest period orbits. Before you get too dizzy, I'll go on to the next slide. All right, so that slide was simply the simplest thing. I took the periods and phases of the planets and plotted them as if they were on circular orbits. Of course, even if in reality, if planets start on circular orbits, they're not going to stay there because they're perturbing one another's orbit. So let's define a coordinate system where we have a reference line here. And relative to that reference line, I'm going to plot the position, the phase of two planets. So that's this angle. So the planet on the longer period orbit is in dashed line here. So it starts at 0 degrees, and the other planet starts at 180 degrees. And they're both starting on circular orbits here of semi-major axis 1.65 and just under 1 AU. All right, so as they orbit around, the inner planet catches up to the outer planet, and then they tug on one another. Okay, this is just the 1/r² force law. I'm going to show little to no equations in this talk, even though it's about orbital mechanics. So just, 1/r² force law. That's all you need to know. You can plug that into a numerical integrator of your choice. That's what I did when I modeled these systems, and then you just update the positions and velocities as the planets go around. Okay, so you have semi-major axes. As the planet catches up to one another, they pull on each other more strongly. And then as they pass one another, they reach the same phase. They've traded a certain amount of semi-major axis with one another. So it's a very small scale you see here. So it's a little blip of first order perturbation. So pretty much they're just going on a Keplerian orbit around the star, but a very small deflection occurs as they pass one another. So also, as they pass one another, their eccentricities no longer stay circular, but they give each other a few 10⁻³ kick. So these happen to be Jupiter mass planets that I put around the sun-like star. And if you continue such a numerical treatment of it forward in time, you see they'll pass each other here, and then they'll pass each other here next time, and then they'll pass each other over here. And then, so they just start sampling their kicks all over around the star. And so then, since these kicks are rather random as they go past each other, the semi-major axis just varies a small amount, less than 1%. And so the semi-major axis does not build up to anything, even though they continue to kick each other. It does so incoherently and does not build up to unbinding each other. On the other hand, this time I've set the orbital eccentricities non-zero at the beginning, and then they actually torque one another, so that you see a slow drift in semi-major orbital eccentricity for both these planets. So that too does not make them go unstable. That will have a near sinusoidal pattern on thousands of orbit timescales. All right, so this one, I put a period ratio of 2.44 to get these particular semi-major axes. And it's near a 5:2, which is why you see some variation every 5th transit of the inner planet, but it's not very coherent. All right, in contrast, near resonant orbits, they pass each other here. Now I've set this planet up at 1.46, so it's going to go around twice. The inner planet goes around twice, and the outer planet goes around once, and they encounter each other on the same side of the star. Then the kick is very similar both times. And so you see that they pass each other here, then here, then here, then here, and it builds up on the same side of the star because the orbital period is an integer ratio. And therefore, the semi-major axes do change quite a lot, by a few percent, and the eccentricities vary on that same time scale. Now we're starting to see something, because these are about 1-year orbits, and this is a 30-year integration. Now just scale that down to a Kepler system with just a few-day orbit, and then you can see this. You can see these variations manifesting as orbital period changes. So here's one of the cleanest examples of that very thing early on in the mission from Kepler 18. It's a 7-day planet and a 14-day planet. And now I'm plotting something more observationally focused, which is called O minus C. It's the observed time of a transit minus what you would have calculated if it was a linear ephemeris. Ephemeris is a fancy term for a table that tells you when the transit times are. So if you expected that to be linear, in other words, the period to be constant, then this would be a flat line. But what you see instead is the transit arrives late by 5 minutes or early by 5 minutes on top of a 7-day signal. So that's less than apart in 1,000. So the orbital period is changing by less than a part in 1,000, but we can very clearly see that in data. And that's because the sides, the ingress and egress that Raphael showed was, they're just so steep. So you shift the planet a little bit and a data point falls in the outer transit or in transit, and then you very clearly see that. All right, so why is it varying like that? Well, they're near a 2-to-1 ratio. So just the same thing that I showed you, they're building up on this time scale. Here's what it looks like. Inner planet goes around a little bit more than twice every one orbit of the outer planet. And therefore they pass each other over here on the next pass. And so it's a rather coherent kick they receive to one another. In fact, I'll call this the line of conjunctions, where they are lined up with the star. And since that changes each time they pass one another, there's a certain frequency at which this line of conjunctions sweeps around the star. I'll call that the great inequality after something in the solar system, Jupiter and Saturn. So that there's a frequency at which this sweeps around, and you can compute it by 2 times the frequency, or the reciprocal of the orbital period of the inner planet, minus 1 times the reciprocal of the period of the outer planet. You can write that should be a superscript. So this is a frequency, and then invert that for the period. The period of this line of conjunction sweeping around is every 270 days. And so that's the period at which we should expect to see the sinusoid complete. So this is what the data show. And you can Fourier transform that, or just eyeball it since it's such high signal to noise. So here's the frequency in cycles per day, and the dotted line shows you where you expect the great inequality frequency, and that's exactly where the peak of these 2 frequencies is. So the great inequality is detected in exoplanets. And in general, I put a 2 and a 1 in these 2 spots, but you could have any resonance, any small integers could be plugged in here and get the transit timing period. All right, so for this system, we have another planet interior that's not in resonance with them. So it's these 2 planets that are resonating, and we can derive the masses from this just by fitting numerical integrations to the data and checking the scale of those. And so that's what I did for this paper, Cochrane et al., and got these masses. Cochrane also pursued radial velocity follow-up, so the other dynamical method, and got these masses, and they agreed to about 2 sigma. What's more startling is that the orbital eccentricity is measured extremely accurately by this technique. And that's because if they pass each other a little bit closer, they're going to kick each other harder. So then you can very sensitively measure how close they pass one another. All right, so more generally, we can use this timescale argument. I just derived the great inequality frequency. We can use that to validate pairs of planets. We know exactly how far off from a resonance they are spaced, and can compute their periods very precisely. And so plug it in, find what period it is, and then check the transit timing curve to see if they are in the same system and they're perturbing one another. So that confirmed rather early on in the Kepler in 2012, we confirmed these planets. And so I instantly recognized Kepler-30c on the diagram from last talk. So, all right, so one of the more exciting ones was early 2011, when Kepler was still struggling and confirming just about any system. This one came along, Kepler-11, and it had 6 transiting planets. This is just a zoom in of a very small part of the data, and you can see all the different depths and durations of transit. So I'm showing the overhead view of the system here. And then this is from the discovery paper, just the first 450 or 500 days of data. And okay, it's not supposed to jump out at you, but I'll break it down in a minute. So what we saw was this variation here. That was the biggest one. And then some confirming evidence here, and then broadly the sinusoid here and here. Okay, so turned out that there were 5 planets showing transit timing variations. Here's the full data set. So you can see a little bit more clearly that there's some variation there. You do need to take a Fourier transform of these data to convince yourself that. Here, so I should say that the data are derived by taking those transit models and sliding them through the data to get the time. Someone needs to mute, I think. Okay, so yeah, that gives you the error bars on each of these colored points, and then the model is these diamonds. Okay, and then planet F, you see, I just showed you the first 500 days is this variation. Well, it's varying too. So to break it down, what I've done here is over here is the data in the 6-planet model. Over here are the 6-planet model is the same diamonds from this plot. But what I've done is also done 2-planet numerical integrations where I've thrown out the other 4 planets from the system. And so this red line here shows you if you throw away all these planets and you just compute the perturbations from this planet onto the yellow planet, you get this line, and it pretty much reproduces the diamonds. On the other hand, if you look down here at this one, you have light blue and dark blue. So on this green planet, the dark blue is perturbing it and the light blue is perturbing it. They're on either side of it. And they're both contributing to the signal, which is the diamonds. And so what you're supposed to see is that they both contribute, and they contribute linearly, both in the mass of each individual planet, and also they add up perfectly directly. So each pair's effect is simply adds up to the 6-planet model. So this is, and since they're perturbing each other on different timescales, so the dark blue is perturbing on one timescale and the light blue on a different timescale, it's quite separable. There are not large mass correlations between the masses derived for these different planets. All right, so that's Kepler-11. But there are lots and lots of other planets that have observed O-C diagrams, so significantly detected transit timing variations. So that there's about 260 robust detections from this paper. That should be 2016, actually. All right, so we have just a gallery here of some of them. There's some really huge signals. 1,440 minutes is 1 day, so this is almost 1 day signal here. Kepler-9 was an early detection. Here's Kepler-30b and C, the one that we saw earlier. Okay, so it goes on and on. One way to see it is to plot up just the 4-planet systems or the 5- and 6-planet systems. This is a paper that's in prep showing the multi-transiting systems. Okay, in black here are the planets that have a strong sinusoidal signal, significantly detected. The red ones are strong but non-sinusoidal. So in Kepler-11, you see, and then either sinusoidal or non-sinusoidal, but a little bit weaker. In other words, a larger p-value is in yellow. So in Kepler-11, we have a strong sinusoid, two strong non-sinusoidals, and then 2 weaker signals. Kepler-11 is also called KOI 157. So there was 2 target lists for Kepler. One where they were just Kepler objects of interest, which means candidates, and then once they have a Kepler number, that's another stamp of approval by the Kepler team. All right, so you can search for transit timing variations as long as the planet's big enough and produces a deep enough transit. Some of them are not even searched, so the grays and the whites are a little bit too subtle to notice, but a lot of these are gray because there were attempts to find transit timing variations, but they weren't found. So this statistics are 260 transit timing detections in the Kepler data out of 2,599 attempts in this Holzer paper. And then another paper tried even for the ones that don't have an individual transit that's very deep, but they phased together lots of transits and looked for sinusoidal variations. So that one found a rate a little bit higher than 10%. So this is a bit specialized. It doesn't hit every single planet in the catalog, but it does hit the ones that are in multi-planet systems, especially where those planets are close to resonances with each other. One of the neater findings in Kepler are particular systems that have orbital period resonances. Here's Kepler-223, Kepler-80, and then now we have TRAPPIST-1, where there are near resonances. Of course, resonances makes you think of music. So here's a system with a 8 to 6 to 4 to 3 resonance. All the planets, the 4 planets are in resonance, and then that gives you some musical tones that you can make into a ringtone. So this is what Sean Mills made. All right, so then you can answer your phone to that. All right, so some of these are shifted slightly off the resonance, including in TRAPPIST-1, but that's good too, because then it gives us an observable time, the signal repeats on an observable time scale. These resonant chains are special. They're a small fraction of the systems, but nevertheless, there are a bunch of other ones known, both another one from Kepler, one from K2, and then some other techniques as well. So more about TRAPPIST-1. If you form that TTV frequency, like I showed you before, you can get here's the 7 planets of TRAPPIST-1, and you can derive what the frequencies should be. You invert these frequencies and you get 490 days. Notice that they're all right on, these 4 are right on top of each other. What does that mean? Well, it means that 3 planets obey a certain relationship with one another. And before this orbital period was known, these 3 were noticed to be exactly the same. So if you just continue the pattern, you could predict this orbital period to perfect precision. So that was actually helped to discover this planet, is knowing what orbital period to look for a priori to do the resonance. So physically what's going on there is that you have the 7 planets orbiting around. And let's just focus on the outer 3. So when 2 of them pass one another, the other one's on the other side of the star. That's what this frequency ratios mean. So this helps with orbital stability. As 2 planets pass each other, they give each other a kick. If all 3 are giving each other kicks at the same time, that would make it more chaotic. This is also a very natural endpoint of orbital migration. So we start to see something about the origin and early evolution of the system based on the ratios of periods and the ratios and the orientations of phases. So as promised with near resonances, you can see TTV. So here's a data set mostly from Spitzer. The best data are from Spitzer. So it's O-C diagram, and the scale is always minutes. And then here's time. And what we have is the 7 planets torquing one another. So they're showing these signs of transit timing variations. In this data set, it just barely covers, in some cases, it kind of covers the 490 days, but just barely. So there will be more data, and this will be firmed up. But nevertheless, with these data, Grimm et al., of which I was a distant co-author, derived the masses for the planet. So here you are. There's the planet mass versus the radius. The radius is just due to the depth of the signal, as we heard from the last talk, and the mass is coming from the transit timing models that fit these data. So we have a bunch of planets with the masses near Earth. And what's really exciting about this system is, of course, that it's around such a faint star that some of these planets are surely in the habitable zone. So we have Earth mass and radius planets in the habitable zone of a non-sun-like star. All right, so we can zoom out and ask what are the masses from all the planets from Kepler, mainly from Kepler. And here we have an analysis of those. It's mainly the 260 that I mentioned. And Hayden and Lithwick are the dynamicists doing this fit. I was a part of this team down here. So we have mass and radius, and mainly what we're seeing just numerically, we're dominated by sub-Neptunes and super-Earths from Kepler. That's they have masses between 1 and about 10 Earth radii. And what was found was that there's a huge scatter in radius in that region. There's a line if a planet is pure iron, kind of the most astrophysically extreme that you could expect. Rock is much more sensible for a super Earth. Ice just means astrophysical ices. It could be water, but then in a different form of matter once it gets close to the star. These lines here are if you add an atmosphere of hydrogen or helium on top of it. Sorry, the text is very small, but this says 1% hydrogen, helium. So this line is if you add a little atmosphere on top of it, here's a Neptune-like atmosphere of 10%, or even a 20% atmosphere. So you need to add a pretty massive, dynamically significant mass in hydrogen and helium to match some of these really puffy sub-Neptunes. Transit timing variations and radial velocities were two different methods finding slightly different results in the mass radius plane. And I think a number of other dynamicists like me think that there's no contradiction. It's mainly the issue that the radial velocity techniques were going after very short period planets because those are the easier ones to measure by that technique, whereas transit timing variations were pushed towards longer period planets where there's a longer lever arm for torquing the planet and a longer period. So then you change it by a certain fractional amount and you get a larger transit timing variation. So what we have here is comparing some radial velocity detections of the planets to the other dynamical effects, transit timing variations. And now it's color coded by the flux that the planet receives. So here's the Earth, 10 times the Earth, 100 times, and 1,000 times the Earth's flux impinging on the planet. And what you see is mass, here's 1 to 10 Earth masses and this big scatter I mentioned. So at the bottom of the scatter, those ones that are consistent with Earth composition, they're almost all very hot. So they've probably just lost their atmosphere by getting it blown off by the star. It's 1,000 times more flux than the Earth receives. So it could, if you took one of these planets and pushed them towards the star that much, they would just become a planet like that by losing their atmosphere. So these planets are robust, even though they're 6 Earth radii and only a couple Earth masses. That's just a nice result from transit timing variations, that there exists such puffy sub-Neptunes. Down here we have the TRAPPIST-7. So right now the two dynamical methods are in this region of small planets. They are coming in rather even. It's mainly a function of, even though TTVs only are seeing TTVs on about 10% of the systems, well, you just have the data in the bag. You don't have to do anything more. Whereas radial velocity, you have to go out and spend a lot of telescope time to measure them. So it's been harder for radial velocity to catch up. TESS will probably change the balance of power here because it'll be much easier to follow things up by radial velocity relative to Kepler discoveries. And TTV's data set will be very short. So we'll have to push on and learn how to do efficient TTV follow-up as well. All right. So now I'm going to talk about the other thing, which was by many expected to be what transit timing variations was supposed to do for exoplanets. It has achieved it, but compared to the characterization side, it's much slower. And the main physical reason is the following. To detect an exoplanet by transit timing variation, there's a strong degeneracy between mass and orbital eccentricity. So if you have two planets near a resonance, they can perturb each other either by being massive or by having an orbit that swoops by really close because of the 1/r² force law. If you just come a little bit closer, then you can kick it a lot harder. So here's two different systems. Both of them have periods of 10 and 15 days. And I'll just read off the caption here. This is from a review article Eric Egel and I wrote. So it's Eric's figure And what he says is, in green, you have two low eccentricity, so nearly circular planets, and they have a mass ratio of 10 to the minus 6 the star. So that's a little bit lower than the Earth. So very small, but nevertheless, it's a larger mass ratio. Whereas if you pump up their eccentricities to 0.04 and go with 10 times smaller mass, 10 to the minus 7 solar mass, you get these the red curves. So the main difference, as you can see, is these short time scale effects. So we dubbed that in the Kepler 9 article. We saw that effect and called it chopping. So it's like even and odd transits are chopping back and forth in a zigzag way. So here, with a near 3 to 2 system, you have sets of 3 transits on the inner planet, sets of 2 transits on the outer planet, where this chopping effect happens. So this is a result of just the planets passing each other, and on that time scale, you can see them pass each other and kick each other. Whereas if you make them more eccentric, they won't kick each other as hard, but their torque is relatively high. The long-term torque can be just as high. So then you see a smoother variation if you're more eccentric and lower mass in this particular configuration. All right, but if you have noisy data, you're probably not going to recover that small amplitude chopping. So then you'll have a degeneracy. The data will not be able to tell the difference between these two orbital period ratios. All right, enter Kepler 19. That was a paper back in the relatively early days of Kepler, where we had about 600 days of data and saw this sinusoid. So as I just mentioned, the noise is too high to notice any chopping. So what we were left with was a list of different possibilities, and this is just a subset of the list. So it's possible orbits for these planets could be just inside or just outside the inner 2 to 3, just inside or outside the 2 to 1, or some of the higher order resonances outside. So we basically don't know what the orbital period or the mass or the eccentricity of the planet is, just that there was a second planet somewhere. I mean, it could even be a planet sharing the same orbital period, just 60 degrees off in phase, or a moon. Yeah, it's very hard to tell from a sinusoid what could be going on. However, there was follow-up of this system just this last year, and what they did was, here's the rest of the Kepler data. So this data set chopped off there, and they measured the rest of the transit times and fit a model that fit everything. And importantly, they measured more radial velocities. So this is the original data set, just showed that there were no big stars perturbing the planet. But the extra data set showed, you can see 3 oscillations in here. So what they measured was the mass of the transiting planet, the 9-day planet. They found another planet at 28 days and another at 63 days. This was just over 3 times the orbital period. And so then you can add to this list something that was implicit in the paper, just about any resonance, a little bit off of it, could give this super period, this TTV period. And so this was a clear prediction of an extra planet that panned out, and a bonus, a 3rd planet was found by radial velocities, solely by radial velocities. All right, so this one I would call the first planet apparent through TTVs. All right, so first planet discovered by TTVs was this one. Just the next year by Nesvorny et al. David Nesvorny has a series of papers where he has a search algorithm for what is the perturbing planet for a particular transit timing signal. So what you see here is a very high signal to noise signal, and it's not quite sinusoidal. So there's clearly a dominant oscillation here, but if you Fourier decompose it, you actually find 4 significant frequencies in there in just like 13 data points. So it's very non-sinusoidal. Nevertheless, even with that chopping business, the paper came down to 2 different solutions, this top one and this one, where they didn't know what the orbital period of the perturbing planet was. It was it was offset from certain resonances, but they didn't know exactly which one. However, the signal to noise is high enough that to get the details right, they would need to incline the perturbing planet out of the plane of the first planet. And that would torque the planet, causing its transit to move up the star, which is the bottom panels here. Transit duration variations. All right, so transit duration variations close the case. They showed that here's the signal and the data of the first and the second models. And so then they determined uniquely that the planet has a period of 57 days and its mass is in here somewhere, down here, 0.37 Jupiter masses. All right, so that's the answer, it looks like. So there's two more examples of high signal to noise transit timing discoveries. One is KY-1474, which became Kepler-419. This is Rebecca Dawson et al. And she noticed that there was a Jupiter-sized planet that had the wrong duration. So it had a 67-day orbit, I think, but its duration was too short. That means it's on a very eccentric orbit and it's flying past the star really quickly. And so she derived a very high eccentricity orbit for this one and found that these transit timing variations on the scale of hours meant that there's another body flying by it. It's coming by at periastron right at this time. So here's the radial velocity data set that just came out this year that shows indeed that, Johnson and Dawson et al. Also collected RV data and found this, but a more complete RV data set was just found in which the outer planet is shown to be an 8 Jupiter mass planet at a 670-day orbit. So quite hierarchical. It's not near circular orbits perturbing one another. It's very highly eccentric. All right, the other example along these lines is about a 1-day oscillation in a Neptune-sized transiting planet. And it was found to be accompanied by a resonant giant companion. So what you do is if you have a polynomial fit or a multi-frequency fit here, or some smooth fit, you get this chopping signal. It's a huge variation. This is every other transit goes by 10 sigma away from each other. So 15-minute chopping signal. And this means that the other planet's pretty close by. It turns out that that other planet is in a 22-day orbit. And they also checked the transit duration variations. So this was a very highly precise planet mass detection, 0.67 plus or minus 0.02. And it was found to be the case by Barros et al. They have a radial velocity data set that matches it. So here's the mass that they derived in the orbital period. This is a kind of future work to mention a frontier about tidal decay. So I've just so far been talking about planets passing one another and kicking each other. But what if the star gets involved? How could the star cause the planet's period to vary? Well, it could drag it in with tides. The planet raises a tide on the star, and that moves through the star. A little bit of friction will cause that tidal bulge to lag the planet, and then the planet will get torqued by it towards the star. So one system was found, it has a period of 1.1 days and a mass of 1.4 Jupiter masses, orbiting a little bit more massive than the sun kind of star. And what you see here is O minus C in minutes. And so it's just a parabola so far. It looks like the planet is, it would have transited here after 10 years, but it transited 3 minutes earlier. Okay, so it's on a very slowly decaying orbit with a period derivative of order 10 to the minus 2 seconds per year. So very slowly falling in, and that gives a certain tidal quality factor for the star. So we can characterize the stars this way. So I've introduced transit timing variations as a characterization tool. We have several dozen transiting pairs with masses and orbital eccentricities characterized. We have one system with habitable planet or planets whose mass and radius we know now from this dynamical method. And there's about 100 transit discoveries that have been validated with only rough characterization associated with them. We've found that there's a mass radius difference between sub-Neptunes and super-Earths, and this was an early discovery by TTVs, which is now apparent also just in the raw histogram of planet counts, the Fulton gap. And it looks like tidal decay is on deck for the next big discovery by transit timing variation. All right, thank you. And these slides will be available, so I put that up. And I'll repeat your questions. Do you want to call in, Pete? Okay, back there. The tidal decay does not rely on a second star. It's just the host star itself, which the planet's falling in. But for the Kepler-19 case, you can go read about how we differentiated the two. In principle, you could have another star orbiting around the system that has a 1-year orbit approximately for that system. And that would cause barycenter change for the planet going around the star. It would come closer to the observer and further from the observer. That would create a light time delay effect. So that could be the case for this system. On the other hand, radial velocity measurements show that there's no such star. So you could take radial velocity measurements of the host star and notice it's not moving closer and further away from the observer at the required amplitude. So then that ruled out a second star interpretation for that one. A lot of these candidates that have not been, I showed a grid of TTVs. It could be that there are some of those perturbations are due to second stars. That's a really interesting thing to do, is take follow-up data of all the 260 and see if there's any extra stars in there. I haven't heard of any reports of such. So they're probably dominated by planet-planet perturbations, is what I'm getting at. Yes. I don't think I repeated your question, sorry, but I hope it was clear to people online. Go ahead. Questions about exomoons and whether they're detectable by TTV. Yes, there's a number of papers showing how you would detect them by transit timing variations. How, if you imagine that the moon is so dense that you don't see it, it would still move the planet around. In fact, that was searched more than 10 years ago for HC 209458b. It was a Hubble Space Telescope, very precise transits. So in my opinion, I wouldn't believe it because, as I showed, there's lots of different ways that you can make a certain transit timing variation signal by another planet. So the first detection of an exomoon by transits, I think, would have to be a photometric detection, seeing the moon go across the star on its own as well. So that's being worked on by the Kipping group right now. And so we'll see how they do. Okay. Okay, so the question is, I showed a hierarchical system with about a 10-to-1 period ratio between the two planets. And the question is whether you might be able to tell something about the age of the system, because the inner planet could tidally decay if it's being perturbed by this external body. The answer is certainly, so that you'd call this thing a warm Jupiter at 67 days. And certainly there's been a series of papers on warm Jupiters that they might be from a little bit from 1 AU or further away and cycling, their eccentricities getting pushed up to a level at which they're tidally decaying, and then maybe get a little bit more circular for a while and then tidal decay a little bit more. So in this particular system, I think by now it's characterized well enough to show that it's not cycling to high enough eccentricity to decay, but I'm not confident about that. So it could be one of these systems that's still cycling enough to be decaying. So if you come back in a few billion years, that planet may well be a hot Jupiter.
Okay, we need to move on. If people have more questions, they can please, they can talk to Dan a little bit. So let's thank Dan again. All right, if you were in the first top group, please come down here and line yourselves up.